My name is Riccardo Ferrari, and I'm going to present you a work done with colleagues from Oxford Universities and Amazon Web Services on a Bayesian approach to implement fault-tolerant control in the case of sensory faults. So what are our motivations, the challenges we solve, and what are our contributions here? So why do we need fault-tolerant control? Well, we are mainly interested in robotic applications that are moving from structured environments like factory floors to dynamic ones like exploring a distant planet or driving a car, and maybe not so far in the future, human-robot cooperation. In all these cases, we need fault-tolerant control. And our goal is to implement a model-based one because they are quite powerful, but we need a probabilistic approach to deal with the uncertainties that we mentioned. If we look at the state of the art, Bayesian approaches were indeed introduced for these reasons, and especially the use of dynamic Bayesian networks allow to account for the dynamics of systems. But still, there are challenges that we want to address. We want to develop an integrated FDI FTC approach without an explicit detection step. We want it to make adaptable and with a low computational complexity, but yet interpretable. That is, human operators need to understand what's going on. To understand the reason for the integrated approach, let us look at how a non-integrated approach is working. We have the classical steps of sensor fault causing, first of all, fault detection, then isolation and estimation, and the information there is used to accommodate and reconfigure the system. In an integrated approach, we don't want an explicit detection and isolation, but we continuously estimate parameters describing the fault and use that to continuously adapt the system. It is nothing new, of course, but is the kind of approach we are pursuing. But to add interpretability to this, we need to get back the detection step that we just kicked out, but we're going to implement it differently. We're going to implement it based on the results of the estimation. And the contributions that we are proposing to deal with this are, so for implementing the integrated FDI FTC, we are proposing two different kinds of Bayesian controllers where we implement what we call precision learning. And for the detection step, we are introducing what we call beta residuals. Okay, now let us look more in the detail how we built these two Bayesian controllers. First of all, the problem setting. We start with a state space model. We have a nominal function f for the process dynamics, nominal function g for the output measurements, and in both cases, they are affected by uncertainties q and eta. The fault function is, in this paper, acting only on the measurements. As q and eta are random variables, we can describe the model equivalently in a probabilistic form. So we can introduce the conditional probability of the next state upon the current state and the current input. And for instance, this can be a Gaussian function. And in this case, it is going to have a mean equal to the nominal function f and a covariance. It is the covariance of the process noise. And similarly for the output measurements. We do that because then we can cast the problem in a way where we can build it to be solved as a Bayesian inference case. And the first approach we are using is via the so-called unbiased active inference controller, which was developed by the authors and will be extended here. Active inference is a neuroscience-derived theory that tries to explain how the control loop of the brain, so the homeostasis function, work. And the short story is that the brain hates surprises. Whenever the sensory information that the brain receives are not matching with the internal belief, the mental model that the brain has, then the brain is going to change its belief or to act on the external world in order to change the world. And indeed, this means with the case of a robot that we have a real robot, the external world with some real state, and we have the controller having a possibly simplified model that is described by means of beliefs about the state. which in control systems parlance will be state estimates, what we call X hat, and models of how the measurements Y are generated and how the beliefs should evolve over time. So they can loosely be based on the state space model that we introduced, but actually they can also be more general. So whenever we have measurement coming from the external world, then this is going to update the belief. And whenever the controller generates a new control action, well, okay, this is going to update the external world. So actually, this is something we control engineers already know, because estimation and control is what we do. The interesting thing with active inference anyway is that these two steps are obtained with a single Bayesian inference problem. And the key to do that is to introduce a quantity that is called free energy to quantify the surprise. So the starting point is a model of the system, and again is a probabilistic model, and we assume that the joint probability of the state x, the input u, and y can be written down as the product of this term, where we have a control term, an observation model, and a prior state. The goal of the inference problem is to compute the posterior. So what is the probability of the state and the control action given the measurement y? So said in another term, given the measure y, what should I believe about the world? What I should act upon the world? We could, in theory, use the Bayes rule to compute that, but in practical case, it is too complex. So to keep complexity low, we choose to introduce a variational approximation. So this is standard in active inference. So this probability is approximated locally by another probability on x and u, which further can be expressed as a product of two terms. Now, the idea is that, can we make this approximation very good? So can we make the Kullback-Leibler divergence between that and the true posterior small? Well, if we compute the Kullback-Leibler divergence, then we get an expression with one term called f, which is actually the free energy, so this surprise. Finally, we get this surprise, the difference between what actually is the world and what we believe is the world. In particular cases, Gaussian uncertainties in particular, we can write the free energy in a very nice form because it is a sum of quadratic terms, all the terms that you see here, plus a logarithm. And so what we have? So we have different terms indexed by y, by I, and these are errors, epsilon, that are weighted by the inverse of the covariance matrix. Basically, these are errors on what the brain thinks about x, u, and y, inversely weighted by the covariance of that. So it is like saying, if we're not really sure about something, we don't take that too much into consideration, which is not just common wisdom, it's also how active inference leads to build a controller. Now, these error terms are prediction errors basically on the state, prediction errors on the sensors, and curiously, a prediction error on the control. And the interesting thing is that here is the way that we can actually plug a control law in, because this term is computed as the difference between the belief on the control, what should be the control now, and the term that tells what actually should be the control in order to steer the belief on the state toward a goal. And this function f star can be pretty much anything. For instance, it can be the function that we get from a PI controller or from a QR controller or whatever we want. Now that we have the free energy, we can do two things, and they will lead to the two functionalities of estimation and control. The first thing is to do gradient descent on the belief on the state. So this is going to update our belief and make f smaller because our belief matches better the external world. Or we can do gradient descent on our belief on the control action, and this is going to change the world basically and make again the free energy smaller because now the world is matching our belief. We can cast this problem in a way that probably is easier to see because it's a graphical way. So we can introduce a probabilistic graphic model for the model used by the unbiased active inference controller is this one. So you have round nodes for variables that we don't know in blue, red for the ones that we know, and we have squares for the probabilities. And here we are encoding the probabilities that connect one variable to the other. So one thing that you see is that in the unbiased active inference controller, there is no explicit definition of the transition probability, the model of the dynamics of the system. And this is why we developed a second controller where this transition probability is present. It is here. This means also that we need to add one more variable to the graphs. It is a variable representing the next state. And the key thing is that for this next state, we can introduce a prior, and this prior encodes the goal towards which we want to steer the system. But more details are in the paper if you want to have a look. Now, what we developed so far is not yet a fault-tolerant controller, it's just a controller. To make it fault-tolerant, we need to introduce an ingredient that in our case is precision learning. How precision learning is leading to that? So we need to think that from the point of view of the model that we defined, the sensor fault event is changing the covariance of the measurement error. From the point of view of the model, the probabilistic model, this is what's happening. So to estimate a fault, we can actually estimate continuously online the covariance of the measurement noise. When we get that and we plug it into the free energy, we see that for a sensor that has a high covariance, then this term is going to be small, which means we don't really care for that sensor when we compute the free energy, we ignore it. And this is the way that we make our control law fault-tolerant, because now when we do the gradient descent to estimate or gradient descent to compute the action, the sensor information from that sensor is not taken into account. Of course, in order for this to work, we need to have some redundancy in the sensor. If we have only one sensor, then we are lost. But if we have more than one sensor, we can basically weight them differently based on the inverse of their covariance. There are two ways to do this precision learning. The first is the point mass approach. So the idea would be to do gradient descent directly on the covariance. But this is impractical also because we need then to invert that, because in the formula that you have seen before, we have the inverse of the covariance. So it makes more sense to directly learn the inverse, which is also called the precision. And that's the reason why we call this precision learning. Still, one thing that we need to assure is that we learn a positive definite matrix. In order to that, we can introduce a reparameterization. For instance, we express the precision as the exponential function of something, and we learn a parameter of that exponential, and that guarantees that is positive definite. Another way to do that, more rich actually, is not to learn a value, but to learn the distribution that generated the value, and that's what is the Bayesian approach. To do that, we assume a prior on this distribution. That is, the distribution is a gamma distribution, which is quite used assumption for covariances. Then learning it means computing its posterior based on the data that we have. And the posterior gets this formula, which means that if we online we compute this formula continuously, we estimate our we update our estimate of the covariance sigma. Now this is for the scalar case, but for the n-dimensional case, we can have an equivalent formulation using the Wishart distribution in place of the gamma. So again, graphically, point mass approach, we estimate a value. Bayesian approach, we estimate the entire distribution. Now, with these ingredients, we have fault-tolerant control. We have adaptation. What we miss is interpretability. So how to inform a human operator something is going wrong. The intuition here is that the expected value of the gamma distribution that we just introduced is equal to the ratio of its two parameters, alpha over beta. Of the two parameters, alpha is not interesting for us, But beta is because beta will become high when the precision is low. That means when a sensor is faulty. So beta can be our residual. And that's the way we call them, beta residuals. We just need to define a threshold. So the idea is to get data that is labeled, so we know when data is faulty or healthy, compute beta for that, and then fit a logistic regression on that, which is basically a sigmoid activation function with values between 0 and 1, which can be interpreted as the probability that the data that we see now is healthy or faulty. Then online, we take data from our system. We don't know if it is healthy or faulty, of course. We do precision learning. We get the beta. We compute a logistic function. And then we compare that against a threshold, which is between 0 and 1 and can be interpreted as a probability, which means it's a sort of confidence level that the system is healthy or faulty. Okay, so we tested this idea against a couple of benchmarks from the literature. As system, we used a tracking controller for cruise control. So a simplified model of vehicle that needs to track a given speed profile. And we considered a simple model-free approach called easy and fast FDI, and a more complex model-based, observer-based approach that is called here SER-FD. For all the three approaches, we consider all the possible combinations of trajectories, constant linear ramp and sinusoidal, or faults, either a freeze, a sensor injection, or a sensor drift. And this is an example of what happened for the case of sensor injection, for a step on the sensor. So we see that during the fault, the error without any fault-tolerant controller is going to grow very rapidly, the tracking error. But with one of the three controllers, that's going to be smaller. But indeed, if you look, the green line is the one from our approach. That's going to be significantly better than model-based approaches, and of course, also model-free approaches. We run a very high number of simulations, so 100 simulations for every possible combination of trajectories and faults. And for these, we computed in how many cases one method was better than another. With how many times it was statistically significant it was better than another. And again, a precision learning approach with our Bayesian controller was the best method among the one that we tested. And then regarding the beta residual, in order to evaluate that, we compute the receiver operating curve of our approach and the other model-based approach. And we computed area under the curve, which is an indication of how good a classifier is. And in our case, we got a value of 0.9 something against a value of 0.87. So it's about 4 or 5% improvement. So in the end, we presented two different Bayesian controllers, and we used precision learning to make them fault tolerant. Then we introduced beta residual to make the results of these controllers interpretable, to detect the fault for an operator. Future work, a lot. We want to move away from the simplified assumptions of Gaussianity. We want to introduce also more general process faults, and we want to carry out analytical, theoretical detectability analysis. As the last thing, I would like to mention the other authors of this paper, Mohamed Baioumy, Hartemink, and Chris Hawes,